Hello everyone, welcome back. We were looking last time about variation of various properties across a normal shock, and we were looking at variation as a function of Mach number. We will go to the screen there, where we saw that if I look at downstream Mach number as a function of upstream Mach number for a static or normal shock that is stationary, then as I increase my Mach number, as in the incoming flow Mach number with respect to the shock, if that is increasing, we find that the downstream Mach number decreases from close to 1 to something very low. But as we go more and more downstream, as we go to very high Mach numbers, we are finding that the downstream Mach number is tending to become a constant. It is becoming an asymptotic value of some different values for different gamma values which we have here. And if you look at u2 by u1, again that is also going to a constant, okay, in each of these cases. So we can actually find the exact asymptote if we look at analysis, okay. And if I look at T2 by T1 or P2 by P1, the pressure ratio or the temperature ratio, they are not going to any asymptote as we go to high enough Mach numbers, okay. And of course P02 by P01, it looks like it is going to an asymptote. If I go and look at it in log scale, it will look like it is continuously dropping, it is not going to an asymptote here, okay. That will be very clear if I go take delta S by R, which is just log of P02 by P01. If you look at that, it is continuously increasing, okay. So if I go back and look at the previous one, where it is P02 by P01, it is dropping continuously. If I take log of this, it will be some negative value because it is less than 1 in the axis. So we have delta S by R is negative of this, log of P02 by P01 is delta S by R. So you are getting, and you are seeing that it is continuously increasing, it is not going to any asymptotic value. Now I will go back to the very first one, M2 alone, it seems like it is going to a constant. If I look at Mach numbers, if I go above 5 or so, the downstream Mach number across a normal shock is almost the same value always, irrespective of what my incoming Mach flow is, okay. This is the regime where we call hypersonics, where things will go almost the same, okay. If I go to above Mach 7, that is more valid, okay. It is better if it is Mach 7 and above. If you want, you can call it above 5 itself that it is doing that, and u2 by u1 again is almost a constant after that point. We can actually find a value for high Mach number approximation, which is what we are going to start with today, okay. So now we will go to the board and find the asymptotic values for this. So we are thinking about incoming Mach number tending to infinity, that is what we are looking for, okay. And we have this expression m2 square, we have derived all this normal shock relation, I am just writing. We are having this. Now we want to say, if I set m1 tending to infinity, m1 being very large, then this will tend to, I can neglect this 2 with respect to infinity, I will just ignore this 2. So it will tend to something like gamma minus 1 m1 square divided by, in the denominator again this m1 square is very high compared to this gamma minus 1, which is almost like 0.4, 0.3, that kind of number. I can neglect this compared to m1 square. So it will become 2 gamma m1 square, and we find that this is independent of Mach number. That is why you are going to constant value, of course, okay. This is what you are getting, okay. Now if I want to find the asymptotic value for various gamma values, let us say I put gamma equal to 1.4, my this is actually, remember, it is m2 square, okay. M2 square tends to 0.4 by 2.8, which is 4 by 28, 1 by 7, okay. So, if I find my M2, it is 1 by root 7, okay, which is 0.378. Okay. That is the value which our plot would have asymptoted to. If you go back and look at the plot, it will look like that. Okay. But let us not go to the plot, anyway you know it is true. Okay. If I go look at gamma equal to 1.66, which is for monatomic gases, I can say this is exactly equal to 5 by 3. It is not really 1.66, it is actually 1.66666 bar if you want to think about it, right, irrational numbers. Anyways, we will just keep it as 5 by 3, it is easier to work with. Then I am going to say my M2 square will become 2 by 3 divided by 10 by 3, okay, which is 2 by 10, 1 by 5. Okay. So, you are going to get 1 by root 5 as your Mach number for that case. Okay. So, M2 becomes 0.447, this is what you are going to get. Okay. If I look at gamma equal to 1.4 to gamma equal to 1.66, gamma equal to 1.4 gas will have lesser speed of sound, which I said in a way is related to more compressible gas. If I think about it that way, more compressible gas will go to much lower Mach number than a less compressible gas. Okay. Just a feeling you are supposed to develop out of this course. Okay. If it is more compressible, it will be more useful if you are going for serious calculations with gamma changing during your flow, but we are not going to deal with that in our whole course. I will just show you what happens if I change gamma, that is all, and we will let go here. If you go to, in any case there is some course, if you want to have a course called high temperature gas dynamics, there we will think about variation of gamma with temperature. If that is the case, then I have to worry about what happens to the compressibility as the gamma changes. Okay. This is just going to give you a little feel for it. If you ever have a course on high temperature gas dynamics, that will give you a lot more feel for it. I will just leave it there. If you want, you can go read up more on high temperature gas dynamics. Okay. What will happen to pressure ratio? Okay. We had this formula, very easy to remember one. So, we will just keep it this way. This was one of the forms of P2 by P1 we had. Okay. If I look at this, if I say M1 is very big number, I am trying to go to asymptote. So, P2 by P1 for large M1 will tend to, I will neglect this 1 with respect to M square, I will neglect this one also with respect to M square. So, it is just going to become 2 gamma by gamma plus 1 M1 square. If M1 is very high, P2 by P1 is also very high. It is not independent of Mach number, it increases if I keep on increasing Mach number. So, it is not going to go to a constant, okay, that is all. So, it is not going to asymptote, which is what we saw in our plots also. Now, we will go to rho 2 by rho 1, density ratio rho 2 by rho 1. Okay. We had one more nice form EC to work with in this case. Of course, I have already tabulated all the various formulae which you can use. I am just picking one of them which will be very comfortable for this analysis. Okay. So, I am going to take this one and I am going to neglect this 2 with respect to this M1 square. Of course, product multiplying by gamma minus 1 should keep, okay, we want to remove that. So, this comes down to, I will just neglect this 2, and if I neglect this 2, this looks like M1 square will get cancelled and I will just have gamma plus 1 by gamma minus 1. So, this tends to gamma plus 1 by gamma minus 1, this is all you are getting. Now, we will go and look at this again. This says that this is independent of Mach number, my rho 2 by rho 1 goes to a particular asymptotic value. Okay. We did not have a plot for rho 2 by rho 1 specifically in the beginning of the class, but if you look at this, rho 2 by rho 1 is same as u1 by u2. Okay. If rho 2 by rho 1 goes to a constant, u1 by u2 goes to a constant, which means u2 by u1 also goes to a constant, okay, which is what we plotted, and we showed that u2 by u1 goes to a constant anyway. Okay. So, now we will go look at what this number looks like for different gamma values. Okay. If I put gamma equal to 1.4, 2.4 by 0.4, that is going to be 6. Okay. If I go to gamma equal to 5 by 3, which is officially 1.6666, okay, we will just keep it that way. Rho 2 by rho 1 will be 8 by 3 divided by 2 by 3, that will be 4. Okay. What are we seeing here? I already told you, when gamma decreases, it is more compressible gas. So, what we are seeing is, if I have an infinite strength shock, then I can compress a gas to 6 times its original density, while if it is a less compressible gas, it is going to go to lesser compression ratio, cannot go to very high compressibility. This is why I am saying gamma is in a way a measure of compressibility. Okay. In a way, I will not tell that it is exact as of now, it is slightly, in a way it is correct, it is not always true. Okay. There is also a molecular weight factor inside if I want to think about speed of sound. Okay. But anyways, gamma is in a way related to how compressible the gas is, to some extent, rough measure, it works reasonably well. Okay. If this is the case, what will happen to my velocity? This is going to be equal to u1 by u2. Velocity goes to 1/4 here, velocity goes to 1/6 here, that is what is happening here. Okay. So, we have already looked at, I will just write here u1 by u2, then I will say I have also looked at asymptote for velocity ratio, I do not need to deal with it separately. What happens to T2 by T1? Okay. I will pick a particular relation, actually we can even pick, I am not going by the notes now, I am going to just go free form writing 1 plus, oh this is going to be more complex, so I have to go by the notes, that is all. Okay, we will go back by the notes, because I will get a m2 square here, then it will be m2 and m1 I have to link, let us not do it that way, I will just go gamma plus 1 by gamma minus 1 plus p2 by p1 divided by gamma plus 1 by gamma minus 1 times p2 by p1 plus 1. We had such a relation. Okay. Oh no, I made a mistake here, this is not right. This happens to be density ratio, whatever I wrote now was density ratio. Pressure temperature ratio is P1 by P2 with a plus sign in front of it. This is correct. This is T2 by T1. We had this formula already. I made a mistake when I was in a hurry. Okay. All this time we have been doing what happens when Mach number tends to infinity. Suddenly I am writing an expression in terms of P2 by P1 and P1 by P2. Why? Because I already know from here that if Mach number tends to infinity, P2 by P1 tends to infinity. So, I will take the shortcut, instead of substituting all the expressions here, it will be very complex. So, I am just taking a shortcut saying P2 by P1 goes to infinity. If I say that this is very high compared to this number, so I will neglect this. So, this will tend to P2 by P1 divided by, now this is there and this is P1 by P2, this is 1 by infinity. So, this is very small number compared to this. So, I will keep this one. This is what I have, but there is no luck, P2 by P1 is going to tend to infinity. So, T2 by T1 will also tend to infinity, but not as fast as the other one, because this number is always more than 1. We just did some calculations roughly, we found that that is 6 for gamma equal to 1.4. Okay. So, this will be going up slower, temperature goes up slower across a shock compared to pressure, pressure goes up faster, that is what you are seeing here anyway, which is what we saw in the plots. So, that brings us to the end of discussion on normal shocks that are stationary. Ideally, I have to go at this point and start solving numerical examples, which I will do after we go to moving shocks. After we finish moving shocks, I want to give you a little more feel for moving shocks than what is given in most of the books, and after that we will go and start doing numerical examples. That is a little better. That gives you a different feel for what can be done. But in case I want to solve a problem, typically what will be given will be, there will be compressible flows tables, which we already said there are tables like this available. We said that we will use isentropic flow tables, that is what we did before. Now I am saying there are also normal shock tables for compressible flows already available. They deal with only stationary normal shocks, not moving normal shocks. Stationary normal shocks tables are available. Okay. So what they give will be, for each gamma, typically they will give 3 gammas, 1.3, 1.4 and 5/3, 1.666. These are the 3 values for which they will give data typically. Okay. What they will have will be m1 as the input variable, and they will give you m2, p2 by p1, t2 by t1, p02 by p01, p02 by p1. These are the things they will typically give you. Okay. There are some more things where they will give you rho 2 by rho 1, but I think it is unnecessary. If I know p2 by p1 and t2 by t1, I can find rho 2 by rho 1, as long as my gas does not change its molecular weight during the shock case. Okay. That is not the case in our ordinary gas dynamics, so we can very well say that there is no reaction during a shock. Okay. In that case, I can say that I can get rho 2 by rho 1 directly here. So I do not need to have a tables which has rho 2 by rho 1 also, because P equal to rho RT is valid before and after. So P2 by P1 divided by T2 by T1 will be my rho 2 by rho 1. Okay. And there is one special thing, P02 by P1, it will be very helpful in solving problems, we will see that. Okay. If I want, when will I use this P02 by P01? To find entropy jump. Okay. Delta S is minus log of this value. Okay. You have to of course know in your tables whether they are giving it as P02 by P01 or P01 by P02. They will give you different books, will give you different things. You have to know what is written there on the top. Okay. And you have to of course get used to picking the correct gamma page. Each gamma will be one page typically. So you have to look the correct page, otherwise you will make a lot of mistakes. This is what happens in most of the exams, people will just take the wrong tables, and because of that they will get wrong results. Okay. Anyways, we will go to numerical solutions later. Okay. Currently we will switch to moving shocks. It gives you a little more feel for waves in gases. Okay. So I am going to start with moving shocks, and I am going to assume that there is a shock moving and it is moving into still air or still gas, no movement in the gas. I am going to assume the gas is stationary till the shock comes in. Okay. So I am going to draw, still we are in 1D world, I am going to draw a 1D duct where there is a shock moving with some wave velocity, I am going to call it Ws, velocity of the shock, okay, wave velocity. And I am going to say, I have to be careful about using variables. I want 2 different reference frames. So I have to compare, I have to go from one reference frame to the other. Till now we have been solving problem with reference frame fixed on the shock, that is I am sitting on the shock, I see that the incoming flow is coming with some Mach number and it is going out with a lesser Mach number, that is what we have been seeing till now. Now I am going to say I am sitting on the outside, as in say on the duct, on the tube or on the ground, and there is a shock moving, stationary gas, shock is moving, and this is a set of compression waves, that is what we said a shock is. So what does that mean? It is a strong compression wave coming in. What will happen really behind it? Flow will follow, right? It is like this snake example, there is a snake, everybody run, and that is the information that is going, they are all running along this way. There is too much crowd there, less crowd here, everybody wants to go this way, that is the feel, right. So I know that the velocity behind is going to be this way, and here I am going to say, now I am being careful using correct variables, I am using V1 here, we will stick to U as the velocity in the reference frame where shock is stationary. Okay, we will keep that as the reference. I am going to say shock stationary. In this reference frame I will call the velocity is u, in the other reference frame I will call the velocity is v. This is the reason why we chose volume to be v cross, okay. And here I am going to have a velocity v2, some velocity v2, okay. And just because I switched my reference frame, the p2s and t2s will not be any different, right. Shock is just a shock, it does not care who is looking at it, whether somebody sitting on the shock is looking at the shock or somebody standing on the ground is looking at the shock, shock does not care, okay. Shock is just a shock. So, the pressure ratios, density ratios, velocity ratios, they are all going to be the same as in this, except for velocity I should not have told, okay. Pressure ratio, temperature ratio, density ratio, those will be the same. Velocity depends on reference frame, that is a very important thing in engineering, right. Velocity depends on reference frame. So, now I am choosing one reference frame here and this is another reference frame where I am saying I am stationary with respect to this incoming gas, okay. I am saying there is still air in the room and there is a shock passing by, that is the condition I am looking at. So, that is this case, I am keeping v1, v2 as velocities in that reference frame where it is with respect to lab or ground reference frame, and this one is with respect to the shock. Maybe the shock itself is moving currently, all I know is I am sitting on the shock, and because of that I am going to see some velocity incoming this way, I call that u1, and we know from all the analysis last few weeks we are going to get this to be u2, yeah, and it is less than that value, we know all this already, okay. And T2 by T1, P2 by P1, rho 2 by rho 1, those ratios of thermodynamic properties across the shock does not change with reference frame. So, I will just use the same ratios, that is very important statement I am making here, okay. Now, I want to go from one reference frame to the other. How will I do it? I want to write u1 in terms of v1, easy, right. Change in reference frame is just because of this reference point is now moving with respect to my original reference, right. So, I am going to say that if I add a negative Ws to this whole system, then the shock will become stationary, Ws to the left will make the shock stationary. So, I will add that to all the velocities in this whole frame, anywhere, any analysis I do, all the velocities I will add this. So, I am going to say u1 here is equivalent to v1 minus Ws, and similarly u2 is equal to v2 minus Ws. Okay. A quick check, if I change my reference frame, any difference in a particular reference frame should not change, right. Difference between this to this should be the same as difference between this to this, that you will get directly here. I want to write it in a particular form, so I will put it as u2 minus u1 equal to v2 minus v1, because I want to proceed from this point. I am going to say yes, this is true, right, a quick check. Now, I want to proceed from here and I want to find the value of v2 given v1 is 0, okay. So, I am going to set v1 equal to 0, I will just make it 0. So, my v2 has a relation already, u2 minus u1 in shock fixed coordinates, that will be my v2, that is what I am getting, okay. So, I am going to have v2 equal to u2 minus u1, I want to write it in terms of Mach number. How will I do it? I want to write it as u2 by u1, then I have expressions for u2 by u1, u1 by u2, everything we have expressions. So, I will pull out a u1 and I will have u2 by u1 minus 1. Now, I want to find the value of u1, what will it be? From here I am shifting to here, simple thing, I can just go to math and say v1 was set to be 0, then I will get u1 as w minus of ws, minus is important here, minus ws. or I can say this is stationary, this is moving. Now I am switching reference frame to this, so this will be moving this way with the same velocity and this is stationary. So it is minus, so it is just coming out directly. So I will rewrite this as Ws times, I will take the minus sign into the bracket, it will become 1 minus u2 by u1, that will become my expression, where u2 by u1 is in shock fixed coordinates. We know everything about shock fixed coordinate properties, we already thrashed it out like last 4 classes, 5 classes. Okay. So now all we have to do is just start substituting things inside. Only one question, Ws is the velocity of the shock. Do we know the value? In a way we know the value, because I have been dealing with u1 all this time. How will I write u1 in terms of say Mach number? u1 can be written as m1a1. Okay. Now I know u1 is equal to minus Ws, okay, and I have already used up the minus sign, so it should just become m1a1. I have already used up the minus sign and the minus sign went into this to flip the terms the other way. Okay. So I am going to say this is equal to m1a1. Now I will go and write a better expression. Okay. I am picking up one of the relations which we wrote before, it should be 2 gamma. This expression I never wrote separately, but this comes from whatever we wrote today for P2 by P1 when we did the asymptotic analysis. 1 plus 2 gamma by gamma plus 1 times m square minus 1 will give you this form. I just rearranged that term to get to this, nothing great, you can get to this form, it is not very difficult to get. Okay. So I have rewritten m1 square I have rewritten and then put a half power on top of it. So I got to this expression. Why did I go to P2 by P1? In reality, when we want to create a moving shock, the way to create it is to create a pressure differential. If the pressure differential is strong enough, then I am going to form a moving compression wave, which I am going past myself, I have to wait for this to happen in shock tubes case, but anyway I will go ahead and tell you that if there is a whole bunch of compression waves come together, they form a strong thin layer called this shock. Okay. We will go into details of this again later, I will just tell you now that a whole bunch of compression waves together is what forms this thin layer called shock. Okay. And now if I know my P2 by P1 that is caused because of this shock, okay, then I can tell what will be the speed at which this shock will move given A1 and the gas in which it is moving. Okay. I should know what is the temperature of the whatever stationary gas, and the stationary gas is gamma value, I need to know these two, and the P2 by P1, which is what is typically referred to as the strength of the shock. Okay. How much compression can the shock give, that is called the strength of the shock. Okay. So if I give the strength of the shock and in what medium is it travelling, we can tell at what speed it will travel. Okay. That is the idea. Okay. That is why we write it like this. So most of the moving shock expressions I am going to show you are all going to be in P2 by P1, okay, very useful in P2 by P1 form. So the next one we already left it half done, V2 is Ws times 1 minus u2 by u1, which can be written as Ws times 1 minus rho 1 by rho 2. We already wrote an expression for rho 2 by rho 1, okay, in terms of P2 by P1. Now I just going to invert that expression and I am going to write it. So my expression Ws, I am going to substitute the top one, So, now we want to go again do this two extremes of the analysis, two extremes of the formulae. I am going to say, what if my shock is very weak? Okay, it is going to cause a very small pressure jump, a weak compression wave, extremely weak compression wave. If I pick that particular case, if it is a weak compression wave, I can say that my P2 by P1 is approximately 1. So, let us say we will set the ultimate weak shock will be P2 by P1 equal to 1 or tending to 1 is what I have to do really. Let us say we will make it equal to 1. I want to see what happens to my Ws. Okay. Actually, we will look at V2 first because the formula is just right above. V2 will tend to, what will happen? That will become 1, this will become 1. It so happens that P2 by P1 will become 1, gamma plus 1 by gamma minus 1 plus 1, numerator also gamma plus 1 by gamma minus 1 plus 1. So, these two will just become 1 overall, 1 minus 1 it becomes 0. So, my V2 tends to 0. That means, if it is a very weak compression wave, there is no flow behind it. Now, what is the speed at which this wave will travel? That is the next question. Ws. I want to find what it tends to. I am going to look at this top expression and again I am going to set P2 by P1 equal to 1. What is going to happen? P2 by P1 becomes 1, gamma plus 1, both the denominators are the same, 2 gamma. So, it will be just add the numerators, gamma plus 1 plus gamma minus 1, minus 1 and plus 1 cancels, 2 gamma by 2 gamma becomes 1, square root of 1 is 1. So, it becomes A1. So, what happens is, if I have a very weak compression wave, it is going to travel at speed of sound in that medium and it may not change any flow, as in no pressure jump, no velocity jump. That is what you are going to get to. Okay. If it is very weak, if it is anything more than P2 by P1 equal to 1, then velocity will not be 0 and I will have slightly stronger than speed of sound as the shock strength. Okay. So, if I have, I already told you this ahead once, I will tell you again, if I have a case where 2-3 shock waves, 2-3 compression waves, weak compression waves come together, then they will get together. I will not tell you how currently it gets together, we will just keep it like that. We will go and do this analysis again when we go and deal with shock tubes. Okay. When the shocks come together, when the compression waves come together, they will tend to overlap one on top of the other and become one strong wave. If there are some 10 waves, they all will coalesce to form one strong wave. It will still be that thin shock wave as far as our gas dynamics assumption is concerned. Okay. It will be reasonably thin. Okay. If that happens, then my P2 by P1 is the overall, it should actually be P2 by P1 multiplied by P3 by P2 multiplied by P4 by P3, like that. Overall it will become P4 by P1 or something, or Pn by P1 if there are n waves, whatever. Okay. So, overall that P2 by P1 across that whole set of waves together will not be 1, it will be strong. Okay. When that happens, this is not really true, it will be moving with some reasonably high speed. At what speed? We will go look at it. If P2 by P1 is anything more than 1, what will happen? This number will not be 1 but higher. Okay. If this number is higher, then my speed of the shock is going to be more than A1, it is going to travel supersonic. Okay. Any compression wave, if it has any reasonable compression, anything more than 1 P2 by P1 will move supersonic. Okay. That is what we are seeing here. Okay. Opposite is true for expansion waves, we will not deal with it right now, but we will go to expansion when we have to. First we will deal with all compressions, then we will go deal with all expansions. Okay. So, this is one extreme of the case, we said P2 by P1 tending to 1, very weak compression waves. Now, we will look at strong compression waves, really strong compression waves, what will happen there. we have to do the same kind of analysis as before. We are going to do the asymptotic analysis, right. We are going to set that P2 by P1 tends to infinity, very large values, and we want to see what is the effect. Okay. The first one we want to do is Ws. I will write it again here. I have this, and I am going to say this tends to infinity, which means I will neglect the other term. So, I am going to get to only the first term remaining, roughly, rough estimate. I will just say it tends to, that is more mathematically correct. We will just say it tends to this for large values of P2 by P1, which means if I keep on increasing my P2 by P1, my shock Mach number, if I want to call it as a shock Mach number, shock velocity divided by A1, I will use it that way. Okay. Now, I will put one more term here, I will call the, actually I will write it separately, I do not want to rewrite everything. This one tends to square root of gamma plus 1 by 2 gamma times P2 by P1. This is what it will come down to. Okay. And we are seeing that if my compression gets stronger and stronger, my shock Mach number will keep on increasing. There is no limit to this, it is not asymptotic to any value, okay. It will keep on increasing. Now, the next thing is we have to do this analysis for V2 by V1, V2 by A1. I want to call this V2 by A1. I could do it as V2 by A2 also. Okay. We will currently do it as V2 by A1, and then we will look at A2 by V2 by A2. Okay. From whatever we wrote before, I can say that I will just directly write the tending to thing. Okay. Gamma plus 1 by 2 gamma times P2 by P1. This one just comes from Ws, whatever is here is exactly here. Okay. Now, the remaining term is 1 minus U2 by U1, that is going to tend to 1 minus gamma minus 1 by gamma plus 1. Okay. This is what it should become. Okay. So, if I set P2 by P1 as very large, you should get to this particular formula. Okay. Now, once I have this, now I just have to simplify this, it is going to, this whole bracket is going to become 2 by gamma plus 1. Is going to become 2 by gamma plus 1, because this gamma will get cancelled with minus gamma there, minus gamma plus 1 is what is there. So, it will become 2 by gamma plus 1. Okay. So, I will get to this particular form. Now, we just have to write it this gamma plus 1 and square root of gamma plus 1 inside, simplify this, you will get to 2 by gamma times gamma plus 1 P2 by P1. This is what we are getting. Again, we are seeing that the induced velocity, I am dividing by A1, this is not like Mach number behind the shock, it is not really that. Okay. I am dividing by A1, we have to go and divide by A2 next, we will do it. Okay. If I divide by A1, V2 by A1, then I am getting that particular value will keep on increasing forever. For a given A1, if I keep on increasing my compression, my V2 keeps on increasing. If I have a stronger shock, the flow induced by the stronger shock will be higher, that is what we are having. Okay. In all this analysis, we have assumed V1 equal to 0. Okay. If V1 is not 0, really nothing goes wrong, we just have to keep track of what is the value of V1 all the time. We will go and do a numerical example next class, okay, where we will see what if V1 is not equal to 0. Then we just have to keep track of it, the values will be much higher, and that is all will happen, okay, nothing special. Now, we will look at I want to make this become M2 as in Mach number. So, I have to look at V2 by A2. Okay. So, I have to multiply this with A1 by A2. So, let us find A1 by A2. Okay. I will go to the next page. A1 by A2, it is the same gas, same gamma, same R, I will just remove it. So, it will just become square root of T1 by T2. I do not need to do much about this. Now, we have to write this T1 by T2 in terms of P2 by P1, because we are writing everything in terms of P2 by P1. T1 by T2 is whatever we wrote before for T2 by T1, you have to write it inverted. Okay. So, it is going to be, this is the only place where it is different, it will be P1 by P2 divided by gamma plus 1 by gamma minus 1 plus P2 by P1 whole power half. Okay. This is what you are going to get. So, for large values of P2 by P1, similar analysis, okay, we just want to see what happens when P2 by P1 tends to infinity. A1 by A2 will become, I am saying this is very high, this I will neglect, I will have in the denominator only P2 by P1. In the numerator, this is very small, 1 by infinity, very small. So, I will have only this term. So, I am going to get gamma plus 1 by gamma minus 1 divided by P2 by P1 whole power half. Now, I want to go and write it with the V2 by A1 already we have. V2 by A1 into A1 by A2 is my M2, which is my Mach number of the flow induced due to the shock, that is this value. So, if I take the previous formula which is here, this one, and multiply with whatever we derived just now, I will take this, put it there. Of course, remember that this is only for very large values of P2 by P1. Multiplied by A1 by A2, which is here for large values, again I will put it as square root of So, we are finding that P2 by P1 gets cancelled, okay, which means irrespective of the strength, if the large value, if this is a very strong shock, it goes to one particular final Mach number. Okay. That is why I am doing all this analysis. If it does not go to any asymptote, I will not even be dealing with such a thing. Anyways, we will simplify this further. Inside the square root there is gamma plus 1 which I can cancel. Okay. So, it will come down to square root of 2 by this gamma minus 1 will go to the denominator, there is a gamma already in the denominator. This is the expression you will get finally for, oh I have to put a close bracket, that is this square root of 2 by gamma times gamma minus 1. If I say my gamma is 1.4, if I say I am having air kind of gas, diatomic molecules, then M2 max, I have to also say induced, I will keep on using this induced, okay. This is the induced flow Mach number, maximum possible is going to be equal to what is this, so square root of 2 by 1.4 times 0.4, okay. I am just substituting gamma equal to 1.4 there, and that comes out to be 1.89. If I want to create a supersonic flow by sending a shock wave into a still medium, I can maximum achieve only 1.89, that is what this is telling you finally. Irrespective of whatever be the initial gas temperature, initial whatever be the gas present, I can maximum reach only this if my gamma for the gas happens to be 1.4. The same thing if it is 5 by 3 monatomic gases, this is going to give, I do not want to write the whole thing again, I will just write the final value, that comes out to be 1.34. Okay. If it is a less compressible gas, I cannot induce very high Mach number, okay. It is going to go only slowly, that is what we are seeing here. Okay. If it is a less compressible gas, it will have only lesser velocity, lesser Mach number. I am not talking about velocity here. Okay. Velocity is not this simple. Okay. Velocity is more complex than this. It is not very easy. We will go look at what the plots look like. I just want to write one more expression. We will start the next class with all the plots. I will just write an expression for this whole thing, V2 by VA1 multiplied by A1 by A2, the full expression, not just the large P2 by P1 values. Just write the full thing, and probably that with that we will close today. We will deal with how the function looks like on plot next time. Okay. So, I am going to call it M2 induced. This is induced in V1 equal to 0 gas, remember that. If V1 is not equal to 0, all the formula here are all wrong. I have to keep track of V1. We have made V1 equal to 0. Okay. I will get to something like multiplied by, I am folding and writing here. So, I am multiplying this with gamma plus 1 by gamma minus 1 plus P2 by P1 divided by gamma plus 1 by gamma minus 1 P2 by P1 plus 1. This is my whole expression. Now, I am going to observe something. I am going to say, when my P2 by P1 is close to 1, my V2 was 0, which is what we saw first, right. V2 is 0, that is, if it is a weak compression wave, it does not induce any velocity, that is the first thing we said, which means my M2 induced must be 0, right. And we saw that if it is very, very strong shock, infinitely strong shock, then it is going to induce some finite Mach number finally, which is supersonic we saw. For gamma equal to 1.4, it was 1.89 value. Okay. If that is the case, there was a point where it should have crossed from subsonic to supersonic, right. There must be some P2 by P1 at which it will cross from subsonic to supersonic. That is, if I want to create a supersonic flow behind my shock, my compression ratio for that shock should at least be some value. Okay. How will I find that? I have to set this equal to 1 and find the P2 by P1 for that. I tried solving that from here, it is very complex, because it is P1 by P2, P2 by P1 to the power half, again to the power half here, P2 by P1, P1 by P2, P2 by P1 everywhere. Okay. Not easy to solve, so I resorted to graphical way of doing things. This is the old style, long time back when mathematics was too complex, they just went to plots, easier, just go one direction, now find out the inverse, easy to do, that is what people followed. I will just follow that, simple enough for our course, it is nice, we do not need to invert this, it is not going to be much use anyway. Okay. So, I just want to say that if I create a strong enough shock wave, I may be creating supersonic flow. Most likely I will be creating subsonic flow behind. Okay. We will look at all this next time with plots of these expressions. Every expression I have put up here for moving shock, we will look at plots of it, and then we will see where it goes. Okay. It looks like I have already crossed my time. We will look at the plots, and then we will start inferring items from there, and we will say what does moving shock do to a gas that is stationary. And after that we will go to numerical examples, where we will first solve simple problems of shocks in flow, that is whatever we said we will do later, right. And then we will go to moving shocks, where we will say shock is moving into stationary gas. After that we will say shock is moving into moving gas, moving one way and moving the other way, and we will see what the effects are. Okay. We will do all this hopefully next class, if not we will go over to one more class. Any questions? See you people next time.